So, welcome back, everybody, to our Gamma seminar. Today we have the last day of this winter semester. We have the pleasure to guest Michał Wojtkowiak, who is going to talk about Canonoid transformations, symplectic and contact geometry. So, thank you, Michał, for accepting our invitation. The floor is yours.
Yes, thank you for the invitation. Hello, everyone. I would like to talk about Canonoid transformations, which were the subject of my bachelor's thesis written last year. We will talk about both symplectic and contact geometry today, although we will focus mostly on symplectic just because it's really the starting point for everything that follows. So yes, the talk will be divided into two parts. First, we will introduce all the necessary definitions of the Hamiltonian and locally Hamiltonian vector fields. We'll talk about canonical transformations and why it is useful to generalize to canonoid transformations and how they apply in physics with bi-Hamiltonian systems, master symmetries, and twisted cohomologies. Twisted cohomologies really will be mentioned as a way of classifying the canonoid transformations. And later we will move on to contact geometry. We will import all the definitions from symplectic geometry and fine-tune them to contact regime. We will see that bi-Hamiltonian systems also exist there, and we will introduce symplectization as a potential way of extending the notions introduced in symplectic geometry to contact geometry. So let's start. We've been through all of this many times at this point, but just so we have to start somewhere, and just to fix some notation, we will denote any symplectic manifold by the pair M omega, with omega being the symplectic 2 form. And now, mostly we will focus on smooth structures here. So usually we can assume that M is smooth. And then imposing a smooth function upon this manifold, we get the symplectic Hamiltonian system where all the physics will take place. And we distinguish two important classes of vector fields on this symplectic manifold. The first one are Hamiltonian, locally Hamiltonian vector fields. And these are these fields that, when contracted with the symplectic form, give closed one forms. And we will denote the set of all locally Hamiltonian fields with the subscript LH. A bit stricter condition is that the contraction yields exact one forms, and in such a case the vector field is Hamiltonian, and we denote the set with the subscript H simply. And now, since with every smooth function we can associate a Hamiltonian vector field, we will do so with a map whenever we see a gamma with a subscript, and that will be a Hamiltonian vector field of whatever is in that subscript. And analogously, for locally Hamiltonian fields, we will use gamma twiddle, and whatever one form is in the subscript will be the associated one form of that locally Hamiltonian vector field. And since we will be interested finally with building some tensorial relationships, because usually working with vector fields is easier than working with functions, we will generalize Hamiltonian systems to locally Hamiltonian systems. So instead of the triple M omega H, we will consider the triple M omega gamma, where gamma is a locally Hamiltonian system vector field. Since every Hamiltonian vector field is a locally Hamiltonian vector field, this is just a simple generalization, and we don't lose any information when doing it. So, and it makes our lives easier. So that's why we do it. Now, the well-known notion of canonical transformation in this regime is simply formulated by a diffeomorphism on the symplectic manifold, which preserves the symplectic structure up to some non-zero scalar. Now, depending on the value of that scalar, we distinguish two classes of canonical transformations. We either say that the transformation is strictly canonical when the scalar is the unity, and otherwise we call them non-strictly canonical. This is important because when we go to contact geometry, this condition will change slightly, but the rest will remain somewhat similar. Okay, but since the definition of canonical transformations doesn't even contain the Hamiltonian, it might seem somewhat unphysical. It seems like we lose some information about the dynamics of the system when we simply impose that the transformation must preserve the symplectic form. And as such, we generalize that notion of canonical transformations to canonoid transformations. And we say that the diffeomorphism M is canonoid with respect to some specific Hamiltonian when the push forward of that Hamiltonian's vector field is by itself a Hamiltonian vector field. There is also the locally Hamiltonian variant of this definition. So locally Hamiltonian vector field stays, the Lie derivative of the pulled back symplectic form along that locally Hamiltonian vector field is zero when the diffeomorphism is canonoid.
By the way, Michał,
Yes.
how you could characterize symplectomorphisms by means of Hamiltonian vector fields?
Symplectomorphisms with symplectomorphisms are simply the strictly canonical transformations, if I'm not mistaken.
Yeah, but how you
And
could, what could you say about the transformation of Hamiltonian vector fields with respect to a symplectomorphism?
well, in the case of symplectomorphism, this just is omega. So, well, it doesn't really. I think it doesn't just change. It just doesn't change the
I mean,
Hamiltonian
for
function.
example, what I meant, I will try to, maybe my question is not clear. When you have the Canonoid transformation up, and you have that the transform, that diffeomorphism is a Canonoid transformation with respect to Hamiltonian, yeah? What you have, the condition you have is that the push forward of the Hamiltonian vector field is Hamiltonian, yeah?
Yes.
Okay. So imagine that the push forward of every Hamiltonian is again Hamiltonian.
Yes. Then we have a canonical transformation.
A canonical,
Strictly.
but strictly or no?
I think strictly canonical.
And if it's in a
No?
constant, because you know if
It
it's a
can.
constant, different
Okay. So
from one, maybe the Hamiltonian changes also by a factor, yeah?
okay. So the Hamiltonian changes by that factor, but the field still remains Hamiltonian. Is that
Yeah, yeah,
the
indeed.
okay?
That is, if as much as I can think now is something like that. And if you want an strict, you have to put also conditions on the shape of the Hamiltonian. Yeah, that it would
Mm-hmm.
not be proportional. It should be maybe the same, something like that. So when you have a canonical transformation, you map one certain Hamiltonian into a new Hamiltonian whose function is the pullback of the Hamiltonian function, maybe. But you transform every Hamiltonian function into a new Hamiltonian function. And
Sure.
when this is that by means up to a constant, it will be this. I think that is something like that. But what I'm telling you is that when you have a canonoid, you can think uh, how this condition is far from being canonical, yeah? And the
Hmm.
condition is that for canonoid, you have a certain vector field, which is Hamiltonian, and it's transformed into a new one that is Hamiltonian, yeah? But if you add the same for every Hamiltonian vector field, you can start thinking about canonical transformations of this. This is what I mean. Difference between one and the other. Why canonoid is so general? Yes, because it applies
Hmm.
to one vector field. Yeah, this is
Yes,
the
yes,
the
it's
point, more or less. Thank you. Please go on.
okay. Uh, yeah, going that path, since the push forward of the Hamiltonian vector field is again a Hamiltonian vector field, we can actually say something about that new Hamiltonian. And just a simple calculation shows that the Hamiltonian vector field, the original Hamiltonian vector field, is actually Hamiltonian with respect to a different symplectic structure and a new Hamiltonian. So if we have two vector fields associated by a canonoid transformation, then the original vector field is called bi-Hamiltonian because it is Hamiltonian both with respect to the original symplectic structure and with a new symplectic structure, which is the pullback of the symplectic structure by the canonoid transformation. Yes, and I suppose if that does happen for every single possible Hamiltonian, then we have a canonical transformation, not a canonoid. All right. Since, like I said previously, it's easier to work with vector fields and differential forms, we introduce the definition of a canonoid vector field, and it's simply a vector field such that all elements of its one parameter diffeomorphism group are canonoid. And later we will see that it's fairly simple to classify these instead of the canonoid transformations themselves. Yes, if in so we have some very general theorems for the canonoid transformations. One such theorem is that whenever we have a Hamiltonian system, then there are some equivalent conditions for a vector field to be canonoid. So if we calculate the Lie derivative of the symplectic structure and then contract it with the Hamiltonian vector field, and if we get an exact one form in return for some primitive function k, then we know the original x was canonoid. And then this is also equivalent to saying that the commutator of the Hamiltonian vector field with that field x is a Hamiltonian vector field, and the function that it's associated with is the difference of k and the Lie derivative of the original Hamiltonian along x. And the proof here is actually very simple. We simply take the condition of being Hamiltonian. So since gamma h is Hamiltonian, we can, with respect to the pullback of omega, we can take the derivative along epsilon of both sides. And if we call the function that the new Hamiltonian vector field is Hamiltonian with respect to by f epsilon, then we get the new Hamiltonian is the decay, the derivative of f epsilon at epsilon 0. Yeah, so this is the essentially the Hamiltonianity expressed in a different way. And then the equivalence of the second and third condition is by simple computation. We calculate the commutator of gamma h and x with omega, and we get an exact one form. So this is the definition of a vector field to be Hamiltonian. And this is a very common technique in symplectic geometry to just calculate the contraction with the symplectic form and see what we get on the other side. And this also applies in the contact case, but there are two contractions we need to consider there, which we'll see later. And the same theorem has a local variant. So if we have a canonoid vector field in a locally Hamiltonian system, then we know that the double derivative of the symplectic form, once with respect to that vector field and once with respect to the dynamical vector field, must be 0. And this is equivalent to saying that the commutator is locally Hamiltonian. So previously we had that the commutator needs to be Hamiltonian. Here we have the commutator being locally Hamiltonian. So it's just very analogous. And the proof is also analogous. So we simply take the derivative of the definition of a canonoid transformation with respect to this parameter of the diffeomorphism group. And we get the double Lie derivative. And then going from 2 to 3, we simply use the formula for the Lie derivative along the commutator, just expand these terms and take the differential out, and we get this equality. So if this commutator is a locally Hamiltonian vector field, and its contraction of omega is a closed form, and the right-hand side is 0, and, well, the other way, if the right-hand side is 0, then the left-hand side is 0, and we know from point 2 that that X is canonoid. Now the question arises, why would one even bother with canonoid vector fields in the context of physics? Well, we know that canonical transformations are especially useful in physics, and that's due to Netter's theorem, which says that a constant of motion can be associated with a Hamiltonian vector field, and then that vector field is a symmetry of the Hamiltonian. And furthermore, then that vector field can be associated with a canonical transformation. And the question is whether we can find a similar theorem for canonoid transformations. So are canonoid transformations in any way related to constants of motion? And the answer is yes, but it's a bit more nuanced than that. And to see it, we need to introduce a couple more definitions, namely master symmetries and generators of constants of motion. So we say that a function is a generator of constants of motion of some degree n, which is a positive integer, if for all possible orders up to m, the Lie derivative of that order is non-zero along the dynamical vector field. But the m+1th order Lie derivative along the dynamical vector field is 0. So in other words, the L plus 1 the mth derivative of f is a constant of motion. And a related idea are master symmetries. So these are vector fields such that, again, the Lie derivative up to order m and including order m is non-zero, but the next derivative is 0. So yeah, again, the mth derivative is a symmetry of the Hamiltonian vector field. And these two are strictly related, namely whenever we have some function which is a generator of constants of motion, then its Hamiltonian vector field is a master symmetry of the same degree. So we can jump between these two fairly easily using that gamma map from before. And just to fix some attention, we have an example of such a generator. So if we consider the simplest case of a harmonic oscillator on a one-dimensional real line, and consider the symplectic manifold, which is the cotangent manifold of that real axis, and with the Darboux coordinates, so omega has this form, then of course any function which depends only on the energy of that oscillator will be a constant of motion. And if we just for now remove zero from our symplectic manifold, the generator of such a constant is of this form, with g being some, again, arbitrary function depending on energy. And we have this term proportional to the arctangent of q over p. Now, of course, this is a generator of specifically this kind of constant of motion. Finding the generators of a general constant of motion is more difficult because we need to calculate that repeated, iterated Lie derivative. Nonetheless, this is a valuable example, I think. And just to illustrate that theorem from before, we can associate with this generator a master symmetry, and it has this form, at least for g equals 0. Okay, and to further classify our canonoid transformations, we will also need some cohomological techniques. Well, perhaps these are not strictly necessary, but they do make proofs rather simple and more elegant. So we define twisted so-called boundary and co-boundary operators. With the boundary operator decreases the order of a differential form by contracting it twice with the dynamical vector field and taking a differential in between. And analogously, the co-boundary operator increases the order of the differential form by taking the differential twice and contracting it in between of the dynamical vector field. And then since now we have a co-boundary operator.
Sorry, Michał, one question with these cohomologies, in particular with respect to the twisted. Do you know if there is any Poincaré lemma or something like that for the twisted?
I mean, I believe if the cohomology vanishes, the intuition applies, so every exact form is closed. But I'm not sure if we have well, because the cohomology depends on the dynamical vector field. So
Yes.
we would essentially need some form of Poincaré lemma for every.
That's what I asking,
vector
and
field.
indeed, that when you said it is trivial, yes, the cohomology is equal to 0. That means exactly what you said. But the problem is that when you have the cohomology and we restrict to some open subset of the manifold, yeah, if somehow you can ensure that every closed form in the twisted cohomology will be exact or something like that, or it has applications, or if is there any way to characterize how it works, or which can be the implications, yeah? or that? Do you have an idea? Have you tried to think of it?
So yeah, I tried. Well, I wanted to calculate some cohomologies for some basic examples of dynamical vector fields, but I don't currently have the results ready because yeah, like I said, because everything depends on that gamma. It
Hmm.
it's
Have you
hard.
tried? Yeah, have you tried a particular example? For example, the given before. Yeah, have you tried to work it out and to study how it looks?
Well, I have maybe because I have a an example of just a two-dimensional uh, field, sorry, a
Yeah.
dimensional manifold,
Uh-huh.
and this is um, the general form of an exact one form, and
Yeah.
I suppose
Yeah.
if yeah, it's not very pretty, but if we
Oh, I know.
for example, if we, of course, input like, I don't know, a free particle or something like that,
Yeah. Uh,
then these vanish,
There is
and
something, let me tell you something. There is something even better. Because in many cases, for example, you are using the canonical coordinate, yeah? That
mhm,
when you have a Hamiltonian vector field, you always can locally to in a two-dimensional manifold, yeah? You can
mhm,
always deform or use coordinates if the function has not a zero, okay, it's not critical at a point. You can use this as a coordinate. Yeah.
mhm,
If you use this as a coordinate, the symplectic form will be trivial, almost trivial. So using
okay,
that, you can rewrite this thing, and many of these things will be equal to zero exactly. So doing this stuff and using these coordinates, you will see how is the flow, you will see how everything looks like in this case. And it will be something quite general for Archie. You can try to work what is, to see what is going on. Yeah, for example, with
okay,
one force, with two forces, and things like that. So this is an idea to check it out, how the thing works. I could say that you will have to add some technical assumptions on the form of the Hamiltonian vector field, but they will be. You don't need to assume something very strict. I think that you can assume make some assumptions and to check how it looks, yeah, and to say something about
mhm,
that. Okay, so it's just an idea, yeah? Yeah, you only have to write it in a proper manner, and I think that in low dimensions you should be able to get something easy to solve because this is horrible, yeah? If
yes,
Q and
yes,
P
absolutely,
are checked, yeah, maybe you can do something. Okay, thank you.
okay, I'll look into it. Uh, yeah, so the rest is just analogous to the RAM cohomology in terms of definition. And this, like I said, this gives us a language to very nicely formulate theorems and prove them. So, for example, we can say that a function is a generator of constants of motion of degree at most m when its Lie derivative along the dynamical vector field of order m is a closed or gamma closed zero form. Um, or just that it is a part of the zeroth cohomology. And yeah, the proof is, well, it could be written in one line, I suppose, if we wanted to. Um, right, we just need to check that the m plus one-th order of the Lie derivative along the dynamical vector field is zero. We don't know if the previous ones are zero, so that's why we say that the degree is at most m and not necessarily exactly n. And perhaps a more interesting example of a theorem that classifies canonoid transformations is that the gamma closed one forms classify canonoid transformations pretty much exactly. So if a one form is closed in that twisted cohomology, then its locally Hamiltonian vector field is a canonoid vector field. It generates canonoid transformations. And again, a very simple proof just by using the definition of boundary operators. We get that. So this is just the definition of, or the theorem from before that said the vector field is canonoid when this Lie derivative is zero. And just by expanding the Lie derivative and using the co-boundary operator, we can see that yeah, it's zero only if the differential, the gamma differential of the one form is zero. So when the one form is closed. Yeah, this is the example. So, so this is just the general general form of a gamma exact one form, and in canonical coordinates, and the locally Hamiltonian vector field associated with them. So, of course, all gamma close, or sorry, all gamma exact one forms are gamma closed. So we can be sure that any vector field of this form is a canonoid vector field. And if the first cohomology vanishes, then we can say that this is the general form of any canonoid vector field. And yeah, this does look very, very bad, but if the vector fields have some simple form, then many of these terms vanish even in canonical coordinates. And since f is arbitrary, we can simplify some terms. All right, so that's for the yeah, because like I said, if the first cohomology vanishes, then we have a sort of one-to-one correspondence between canonoid transformations and uh, and constants of generators of constants of motion, because if the first cohomology,
Sorry, Michał, may I question? Have you
yes,
tried to relate the commutator between both cohomology operators?
of the boundary and the co-boundary?
Yeah, yeah.
Yes, I think the that is in the on my thesis somewhere, but
I
the
don't remember. I think so, but I don't remember now.
because I don't remember the result, but the computations were just very long because we had to yeah these contractions repeat and all
Mhm.
of them are equal to zero at finally or something, but I don't remember the result.
Because if they commute or anti-commute, you can relate the image of one with the kernel of the other and do different stuff and start relating to the Poincare lemmas and things of the sort. Maybe we did something, but I don't remember. And I think that we had no time to. Well, I when I took a look at it, I was thinking of making more things about that to explore it in several manners, but there was
Mhm.
no time to go on.
Yes, yes.
So I was just remembering now that I thought about it, but I wasn't sure. But it's something that one can understand, one can try to relate.
Yeah, because in general, I'm very interested in these twisted cohomologies. In if there is some way to expand on that, I'd be very interested in that because yeah, I did work a little bit with cohomologies before, and this seems like an interesting way of classifying these things.
Yeah. Okay. Let's take a look at it at some moment if you want. Thank you.
I think. Um, Yes. So yeah, like I said, so if the cohomology vanishes, then we have sort of a very easy relation between canonoid vector fields and master symmetries. If the cohomology doesn't vanish, so if not all closed forms, yes, if not all locally Hamiltonian if not all canonoid vector fields are associated with a function like this, then the things become a bit more nuanced, but there's still a theorem which connects generators of constants of motion with Canonoid transformations. Namely, if we have a general canonoid vector field associated with some gamma closed one form, and we decompose it into sort of an exact part and a, a rest part, then if that remaining part is closed with respect to the boundary operator, is in the kernel of the boundary operator, then that exact part is a differential of a generator of constants of motion. And furthermore, the constant of motion can be chosen in such a way that its differential is the Lie derivative of that remaining part alpha. So this gives us a way of recovering a constant of motion from a canonoid transformation whenever this kind of decomposition can be made. Yeah, here the proof is slightly longer, but again, we use the well-known technique of contracting the commutator with the symplectic form, and some terms vanish. We get a Lie derivative along gamma of this quantity. And if the commutator vanishes, then we can define a function such that its differential is the Lie derivative of alpha, and the differential of that quantity will be zero. So at least on connected components of the manifold, we can choose f to be constant and equal to dg, or the Lie derivative of g, and then g simply becomes the generator of constants of motion of the first degree, and then f is a constant of motion by extension. Right, so just to finish off the symplectic case, this is a very I like this example because it's somewhat surprising, I think, because we rarely see Hamiltonians of such a form. This is not a pretty Hamiltonian. It contains the root of q plus p to the third power, and the resulting equations of motion are not very pretty again. And canonical transformations, in this case, at least I didn't find any canonical transformations which make this any easier. But we can use a canonoid transformation of this form. And yeah, this, like I said, is not canonical. If we pull back the symplectic form, we do not recover the symplectic form on the other side. But if we push forward the Hamiltonian vector field, we get again a Hamiltonian vector field of this form, and the form and a vector field of the form p dq is the Hamiltonian vector field associated with the free particle. So we get a Hamiltonian vector field which is bi-Hamiltonian, once with respect to this strange expression and once with just simply the free particle Hamiltonian. Yeah, so that's rather, I think, surprising. We can solve the free particle Hamiltonian, and this will tell us something about the previous problem.
Michał, one question, because I don't remember it, maybe we didn't. We tried to study quantum mechanical systems in the the usual stuff that you have affinity dimensional Hilbert space, and you understand it as a symplectic manifold, yeah.
Yes, yes.
And you have Hamiltonian vector fields that they have a Hamiltonian. This is one half of the average value of the function, whatever those, the operator, I mean. This is the Hamiltonian function and things like that. So there is a symplectic approach to quantum mechanics, yeah, in finite
Yes.
dimensional spaces with the Schrödinger equation. Did we study these models, by means of canonoid transformations?
Very briefly. So we did have one example, and uh, and well, it just employed all the techniques that I just explained, but uh, but yeah,
It
it was just
was,
one example.
yeah, it was, we did something like the typical vector fields, maybe the dilatation, I don't remember what the
It
dilatation
was
or the
the
phases, or the phase vector field, yeah?
no, we did the dilation vector field.
Dilation.
Yeah,
Yeah, okay.
yeah.
Maybe, but because no, I think they have a couple of theirs that can be exploited. So else, so it's an example that it could be a little bit full-fledged. I can tell you afterwards how to study to particular example and to more stuff, because here you are all the time studying symplectic form. For instance, you have to study also, for example, the UV4 to make quantizations conditions.
Hmm.
So you could try to study this also. Okay, one day we can talk. Okay, so it's
Okay,
something
great,
that
great.
you can try. Thank you.
Right. So that essentially concludes the symplectic geometry case. But like I said, uh, we can generalize some things to contact geometry, because of course, well, there are many systems which we won't be able to so nicely describe with symplectic geometry. If we have some energy losses, then we are missing a dimension to describe it. So contact geometry seems like the natural next step. And here we do have a lot of well, a lot of analogs from symplectic geometry. So I will denote contact manifolds. I will only talk about coorientable contact manifolds for now. So for us, it will be a pair of W and eta, where eta is the contact form. And again, just imposing a smooth function will give us a contact Hamiltonian system. Now, the definition of a Hamiltonian vector field is slightly more complex. We need to not only consider the contraction by the contact form, but also by the differential of the contact form. And the bottom condition is essentially the same as in the symplectic case, except we have to subtract some term with the Reeb vector field evaluated at the f.
Michał, here's one thing. If you require that the vector field will leave the kernel of eta invariant, that the Lie bracket of the vector field X with the kernel will be a vector field of the kernel, yeah?
Mm-hmm.
So it amounts to this. It's exactly the same. If you demand this condition, the kernel is invariant, yeah. From
Mm-hmm.
this, you can get that the Lie derivative of the vector field with respect to eta will be proportional to eta, because it's the only way to ensure that. And the final, like the function, the Hamiltonian function, the contraction of eta with the vector field, I mean, by given the first thing that it is up, the first equality,
Mm-hmm.
the second one follows. Yeah,
Oh,
because
I
if you
understand.
demand that the Lie derivative of the eta will be some function with the eta, you get that this is you have the sum of, well, the differential. You only have to do the differential of the first one, yeah. You see? The
Mm-hmm.
first
Yes, yes.
equation, and you add the second. Doing so, the left-hand side sum up to the lead derivative of the eta. The right-hand side is minus the red vector field eta with the f of it, on eta. Yeah? So if you define the contraction by f, it follows the second equation exactly. You can write it down. So it's very easy because the only thing you say is the Hamiltonian vector field is something that lives in the kernel of the eta invariant. And this is a condition that does not depend on function, does not depend on anything. The function is just a representative. Once you have the kernel of the eta, the contact distribution, if it's invariant, and you pick up an eta, even locally, this gives you a representation of the vector field by means of functions. Yeah? And you use the functions to study the vector field. So it's something accessory. Yes? So it's like that. These equations are usually the definition, but in reality, they are the consequence of the variance of the kernel of the eta. This is the real geometric thing. And this manner of understanding it allows you to avoid the eta. And it gives you a way of understanding that you are representing the vector fields by means of the function. Because, for every Hamiltonian vector, contact vector field, there is a function, and a function determines uniquely a vector field, yeah? Locally. So this is the way of doing. Okay, so this is something quite interestingly, quite more geometrical than this. Canonical, let us say it this way.
I understand, yeah. All right, so I suppose we could rewrite the definitions here to be nicer. But yeah, like it was said, each smooth function can be associated with a Hamiltonian vector field, just like before. And I will just put a C in the superscript to indicate that we are talking about the contact field. All right, and for a transformation to be canonoid, we get essentially the same condition as with the symplectic case, just with switched notation. The push forward of a Hamiltonian vector field needs to be a Hamiltonian vector field by itself. And then again, just like in the symplectic case, we have a canonical transformation if it is canonoid with respect to all possible Hamiltonians on that manifold. All right, and before we had strictly and non-strictly canonical transformations. Here we have a slightly larger family because the canonical transformation doesn't need to preserve the contact form up to a scalar multiplication. It can preserve it up to any nowhere vanishing function multiplication, which does introduce slight complications, or well, it makes the family larger. And we have bi-Hamiltonian systems, just like in the case of symplectic manifolds. So whenever we have a canonoid transformation, then the pullback of eta is a contact form, and the push forward of some function, the pullback of some function is a new Hamiltonian. So if we push forward the Hamiltonian vector field, we get a Hamiltonian vector field, but also that original Hamiltonian vector field is Hamiltonian with respect to a different contact structure and a different Hamiltonian as well. So this is, again, very similar to the symplectic bi-Hamiltonian systems. And again, in an analogy to the symplectic case, we have a way to check if a vector field is canonoid, and it is canonoid if it commutes with the dynamical vector field, giving another Hamiltonian vector field. just like before. Now, the question is now how to import all the interesting results from the symplectic geometry case into the contact case. And one such way is by symplectizing the contact manifold. So we'll have internal and external symplectization, but since we talk about coordinated manifolds either way, then the external symplectization is sufficient. And we define it in such a way that we just take the product of the contact manifold, and then we impose a symplectic form of this form. So we take the pullback by the projection onto the first component, so onto the contact manifold of the contact form, and we multiply by some factor e to the tau, where tau is the natural coordinate on that real axis. And then we define a new symplectic Hamiltonian. Again, we multiply by the exponent of the natural coordinate. And this natural coordinate doesn't have any specific physical significance, but it does introduce a sort of drift in the Hamiltonian. So if we now took
It
yes.
has a physical meaning. We can discuss it. It's some kind of dissipation.
Okay, yes, but the important part is that if we symplectize a contact manifold, and for example, I perform a canonical transformation on that new symplectic manifold, and we descend back to a contact manifold, it's not always the case that we get a manifold related by canonical transformation in the contact regime. And that's because if we, in general, canonical transformations on the symplectic manifolds can mix that scaling parameter, that tau, with physical coordinates, with momenta and positions. And I think that's the problem, right? So that itself doesn't have any physical interpretation, that mixing of the dissipated tau with physical coordinates.
Really, I'm not sure. I should take a look at it. Indeed, I have several. I have several ideas about how to deal with it. Yeah, but I'm not sure. So sometimes I prefer not to say anything. But it is something that we can discuss someday. Something interesting.
Yes. But yeah, in general, we want to avoid that mixing. So we would like that symplectomorphism or that canonical transformation up in the symplectic world to be
Yeah, sorry, I have a
somehow.
question.
Yes.
Well, why? I mean, you can start. I mean, the contact manifold can be regarded as the one homogeneous symplectic one, where you have like action R without zeros, right? Without zero, right? So you can start like defining the canonoid transformation for contact structures, like simply defining them for one homogeneous symplectic one. When you define this canonoid transformation as a symplectic canonoid transformation that commutes with this action, is it possible?
Yes, that's sort of where I was going, but not in canonoid, but first for canonical. So yes, exactly. The canonical transformation in the symplectic sense must
and
be...
also in this case, you just consider like general contact manifold, and you don't have to start from co-orientable contact manifold.
Co-oriented, yeah.
I mean, Bartosz, that's the idea, the main idea of this.
Okay, yeah.
Yeah, so the canonical transformation needs to be in some way equivariant with respect to that extra coordinate, and specifically if it has this form, then the symplectic, the contact canonical transformation has also a well-defined form. But yeah, but this isn't general for any canonical transformations. And yeah, the situation is slightly gets slightly complicated when we introduce Hamiltonians, because then I suppose we have that extra coordinate, and we have to consider how it interacts with the Hamiltonian, and then the condition of a canonoid transformation is well, it's less, I think, less simple. In particular, I don't actually have it right now, but the idea is to go to the symplectization, find which canonoid transformations are canonoid when after the descent, and then we can say something about all the classification theorems that we had on the symplectic manifold. We can translate to contact manifolds. And yeah, but for now, I think that's all I have prepared. So
thank you very much, Michał. It was very clear. Is there any other comment, remark? Because
is there any? Yeah.
Please go on, Bartosz. Go on. Yeah.
Is there any generalization of symplectic canonoid transformation to Poisson canonoid transformation?
Yeah, I'm not sure about that.
Yes, there is.
Okay, and if so, is there any connection of this twisted cohomology to Poisson cohomology?
Bartosz, I think so, but I'm not sure really now. And it's not about cohomology. It's about this in this manner. I think it was for Poisson, but I'm not sure if I thought of it by myself or it's something that I read. Indeed, I know that they are Poissonoid transformations. Yeah. That's I know there are several results. Yeah, they are, but I'm not sure. Okay, is there any other question?
I think canonoid transformations by themselves are general enough that anywhere where there's a notion of a canonical transformation, a canonoid transformation can be somehow defined. So
there is another thing, Michał, that I didn't tell you, but it could be interesting. And I'm not sure if someone has done of it. But normally, Hamilton-Jacobi equations are understood by means of canonical transformation. Yeah, but since I start with a system, you can use instead of a canonical transformation, a canonoid transformation. So you could get a new Hamilton-Jacobi equations, but it should be more general than the previous one. So have you thought of it, or something like that?
Not yet, but I suppose it would be interesting with consider is all the generating function formalism and stuff like that. Yeah.
Well, Canonoid, because I think I didn't say it, I guess. So it could be interesting, generating functions and Hamilton-Jacobi equations in this manner, and to see how far one can go. Yeah, it's a kind of special formulas adapted to a particular system So it's not that generalist for every case, but if it works, it can be more useful. So it's something that you can think of for your work on it. Okay. Any other question? No. So thank you very much, Michał, and bye to everyone, because this is the last seminar of this semester. We start again next semester. Please take into account that we have Luis Roya Fernandez, is son of the best mathematicians working on Poisson geometry in the world. He has one particular very famous result about the integration of Lie algebras to Lie groupoids, the generalization of the third list theorem. He has lots of things about the integrable system, master symmetries also, well, you did, but in the Poisson realm and things like that. So I recommend you to attend, and he will be exactly in Warsaw. So our first seminar next semester will be hybrid. It will be live and it will be online because Rui will be here. So I invite you, everyone, to see him. And to make comments because he's a very nice and very intelligent guy. Thank you very much.